Hello, welcome to our screencast here for scalability and PySpark and data science. This is a piece of a larger course that we're preparing for doing a data science in the Python language. And so with this point we would have discussed performing Python data science using pandas and scikit-learn. But we're now going to be talking about scalability issues and how we can use the Spark framework together with Python in order to do the same sorts of things on big data. Now, as we said before, Python, NumPy, SciPy, scikit-learn, these are all not transparently scalable. And this is no flaw or defect in these technologies. These are designed to run essentially on a single machine, and these are similar to most other competing technologies as well. So this makes these tools that we've learned already suitable for small to medium-sized data. Enough data that you can easily fit on one particular box. Now, if you're going to scale with these, that can be done, but it means you have to do custom programming. You might have to shard data. You might have to have some of the challenges around distributed computing. One of those challenges is fault tolerance. Efforts to scale, then you're going to have to do some redundancy of your data and processing, or you're going to find a system that's going to be very brittle to failure. So Spark is a technology that is designed to perform cluster computing, and is a cluster computing engine. It's open source. It's designed to be very fast. It is designed to general purpose, so we can do batch SQL type operations, streaming, machine learning, analytics, etc. And it's designed to run with a number of different cluster configurations, the most common one being Hadoop, but also supporting Mesos and running standalone as well. And as far as data is concerned, it supports the Hadoop native Hadoop distributed file system, HDFS, also Amazon S3, as well as Cassandra, HBase, other NoSQL data stores, and many other underlying technologies with a pluggable architecture designed to support more in the future. And it's also easy to code. We can we're going to show a word count example here in this screencast, and it's going to be small. So we are going to show how it's easy to do. Spark came out of the Berkeley AMP Lab. It is actually now a top-level project, and it's very popular. We have a commercial vendor, Databricks, now supporting it, and it's also supported by Hadoop vendors like Cloudera and Hortonworks. And we even have a package repository, which has a lot of add-ons as well. So you can see here, in the last couple of years, Spark's really exploded in its use. It's one of the most active projects out there now, and you can show here how it has great performance for a lot of scan and aggregation with less code size than competing technologies. So how Spark is illustrated here, we have our core Spark API here, and on top of that, that supports a number of different use cases. We have Spark SQL for schema, SQL type operations, Spark Streaming for real-time, ML Lib for machine learning, which we're going to look at later, and graph processing. We also have our Spark core associated with either standalone Yarn/Hadoop or Mesos, and running on a number of different underlying storage technologies. So you can see here that our Spark structure is designed to be pluggable. It is able to do different cluster and distributed technologies, different cluster managers, whether that be Hadoop or Hadoop Yarn, Mesos, etc. And the core engine is going to be shared among many different components. The core is going to rely on the RDD, Resilient Distributed Dataset data model, which is basically a distributed collection of items. Similar to collections we work on in pandas or other technologies, this is going to then be distributed across the cluster. And we're going to have an API, and we're going to be using Python for that API, which there are other options, Scala or Java, but this API is going to be easy to use, and they're going to be shared across different components. The Spark SQL, our Spark Streaming for real-time operations, ML Lib for machine learning, and graph operations. So Spark is designed to do a tightly integrated unified stack, allowing us to combine all these different programming models under one roof. So it's like one-stop shopping. Ideally, this can be the only stack that we really need. So we have different use cases for data scientists and data engineer. As data scientists, we are doing ad hoc exploration, doing analytics on our data, building models, coming up with insight recommendations, etc. Our shells in Python are going to be great for this kind of ad hoc analysis, and we've already been doing this in Python. We can then use rich libraries in Python, and we're going to be able to ideally have interactive development, not waiting around for batch operations, and a unified stack. We can do all with a common API. And from the engineering side, we're going to productize these great ideas that we're coming up with. We're going to be building the infrastructure for data pipelines and processing and all of that. Some of the use cases that we have here are Uyala, which is for video content. They are using Spark and Cassandra together for doing personalized video recommendations. Yahoo, of course, is a pioneer in the area of big data. They are using Spark for news personalization, and they're using MLI for machine learning. In that, they were able to replace 15,000 lines of C++ and able to run a job doing personalization on a very large data set of samples. We have examples here from Alibaba and Netflix. Netflix was able to analyze streaming events, a very large number, 450 billion events per day, and perform personalization recommendations on that. We have other examples here. Tencent, a social network from China. They have an 8,000 node Spark cluster with 400 terabytes per day. Alibaba has a 1 petabyte amount of data for doing distributed image processing. And we have some examples here too for streaming, 1 terabyte per hour, doing analytics. We're able to do this through Lambda Architecture, which is a design pattern for our data infrastructure. And the idea behind the Lambda Architecture is to have a fault-tolerant system that can handle different hardware failures, human error, and this is going to be a layered approach, which is going to allow us to incorporate both batch and real-time needs. The batch layer running at the lowest level is going to manage our master data set, and we're also going to be that data is going to be immutable, like Python. Like in Python, we also see pandas is also immutable data. This is no less true here. However, that's going to enable us to pre-compute batch views that we're going to be able to serve at low latency to our users, and then we're going to you have a speed layer that's going to be highly in memory and able to accommodate low latency requests. So the way this is going to look is that we have new data come in, we have a batch layer for our master data set, we're then going to be creating different views of that batch for the serving layer, and we're also going to be doing a speed layer for in-memory real-time type operations. Now in the past, doing all these steps would require bringing in a lot of different systems. For example, in the Hadoop world, we might bring in Storm for doing our real-time stuff, Hadoop itself, MapReduce for doing our batch analytical processing, and then we might bring in some in-memory operations with Memcached or something else. Again, this is a very challenging system architecture to engineer. Spark is able to bring this all in together, and we're able to get it in a single system. For example, if we're doing like mining of log files, we can use the core Spark functionality to process our data. We can use Spark streaming to do real-time views of that same data. We can also do aggregation of different kinds of views that we can store and batch. So Spark is arguably the best platform for this at the current time. So again, we're bringing in new data, we're doing streaming analytics, batch processing, and aggregated query. So what is this RDD we keep talking about? It stands for Resilient Distributed Data Set, and it's our core data abstraction in Spark. So the D part, distributed, means is that it's going to be partitioned our data across different nodes. As we said before, it's read-only immutable data, and these operations are going to be executed in parallel across these partitions. It's designed to be fault-tolerant. So if we have a loss of a partition, again, we need to build resiliency into the system, and we want to do it efficiently. We don't want to necessarily have to store a bunch of different redundant copies of our data. Instead, we're going to be able to take advantage of the data lineage, able to recompute this data. And we're going to there's basically two different operations on our RDDs. One is transformation. That's a lazy operation. We'll talk about laziness in a minute. That is going to be creating new RDDs. So this is things like transform operations, filter operations, map operations, etc. And then we're going to have actions. And actions are basically going to be getting answers. So we're going to be getting a result or storing data to a new location. Our RDD lifecycle is going to be like this. We're going to create an RDD by, say, loading some data from, say, a file, from a location, say, an HDFS. This is going to then be distributed, this collection, across this RDD. This RDD is then going to be transformed. Let's say, for example, we load in this log file from HDFS. We're going to then filter that. Like, say, for example, we're going to keep lines only starting with error. And then we're going to further filter by keeping only lines containing MySQL. Then the result of that is going to be a new RDD. So in this case, the first filter, we have RDD2. Then we're doing a further filter. That becomes RDD3. And then eventually, of course, we're going to have to extract that. We're going to save the data. And that's going to be an action. Write the result out to a storage. There is then, you see, we're going to read and transform the log file and save the result. Now, the Spark engine does not immediately compute these results. It's lazy. So that means it only does the work when it absolutely has to. In this case, laziness is actually a virtue. Because our transformations are going to be stored as a graph, a DAG, from the base RDD, and then we're going to perform parallel computation on that data. So you can consider then this RDD essentially to be a set of operations or a view on the original data. So the DAG, or the directed acyclic graph, is going to be executed once an action actually occurs, whenever we need to store some data or get some results. Then this laziness is going to allow Spark to optimize the required calculations and also efficiently recover the RDD based on a node failure. This lazy operation, remember, we're creating RDD2 from RDD1 by doing, first we're going to do the create, we're then going to do the filter. Again, these RDDs are created, but no work is actually done until we call an action. In this case, first. First means is we're just going to get the first item in the RDD. Very simple. And the fact that we're being lazy allows us to only do the minimum amount of work required in order to get the first operation, the first item in the RDD. So therefore, we don't need to even read most of the file in this case. And then notice here, first, no execution on the first operation. Second, no execution. Finally, when we call the action, then execute. Then we're going to run the DAG and get our results. Now, because we're talking about big data here, that means if we have a file, that's going to be partitioned. So if we have a 1 gigabyte file, while that's not really big, within our operation, we partition that up into blocks. And that is going to be, by default, 64 MB, but this depends on our cluster. It's going to be based on these partitions from our HDFS blocks if we're running on Hadoop. Then we're going to partition the data and distribute that across the cluster. So we want data locality. So that means is that we're going to run our operations in Spark on the machines that happen to be hosting the data that we want to run on. So that means that we're going to enable parallel process on all of these partitions. Now, a transformation is going to create new partitions. That transformation means is that we're going to take our data, transform it, and that's going to be new data. Again, remember, we don't modify data in place. We're going to be creating new partitions of the new RDD. Now, in our case, with our server.log, we have different partitions of our original log file, only some of which are errors. We're going to be filtering that out in a minute. We're going to be spreading that across this 3-node cluster that we have here. Once we execute our filter operation to take RDD1 and create RDD2, then we're only looking at our filter for lines containing error. So now you see we have uneven partitions. We have 3 in partition 1, but only 1 in partition 3. And when we further filter, we're only looking for items that contain MySQL. Now we have a completely empty partition 2, and we have one item in each of 1 and 3. Now we have a new RDD, RDD3. Remember, we're lazy, so we haven't actually done any actual work yet. Now, we might want to, beyond this, create a 4th RDD, which we're going to do what we call a coalesce, which is basically going to rebalance the partitions. Notice here that we have even partitions now. Now, one thing we do is we collect the lineage of all the transformations that create a given RDD. The advantage of this is that if we lose a partition, we can always rebuild all of that from its lineage. So if we can just read the HDFS block again, apply the transformations, and get the data back. This is very efficient. We're not actually redundantly storing a bunch of operation in order to achieve this kind of fault tolerance, and it allows very little overhead. Now, one thing here is that RDD is transient by default. So once you run the action, if you have not stored your data, then Spark assumes you don't care about it anymore, and it throws it away. So if you need it again, then it can always get to it. It just recomputes it. A lot of times, that's fine. You know, we don't care. We can just, if we need to get that again, we can just recompute it. However, it is useful sometimes to persist the RDD, to keep it in memory so we can refer to it again. Often, if we have an expensive operation, then that can be very useful to do. All right, so we've seen about how RDD is in action. We're going to get an example here of the word count. So word count is kind of the classic hello world example we often see in the world of big data. The word count just basically means we take some text data sources, we get the words, and then we count them. So let's take a look at what this looks like. So now I am running here a IPython notebook here. This is going to be familiar with what you did before, but this is going to be a little bit special because I've run this to run with PySpark, which is going to be the Spark shell that runs in Python. So let's go ahead and take a look at this. I have this running, and we're going to see here that that we have our word count example here. So this is the right here. We see the Jupyter notebook here, and you see here what we're going to do is, and I'm going to run this first cell. Here what we're going to do is we're going to get this environment variable Spark home, and then that Spark home is going to load a text file called readme.md. So I'm going to run that. And what that's going to do is it's going to create a new RDD here called text file. Now, remember, we're executing lazily, so that operation hasn't done anything yet. In fact, it hasn't even looked at readme.md. It doesn't even know if readme.md actually even exists. So in the second cell, we're going to create a new RDD called word counts. And word counts is going to take our text file here, and what it's going to do is going to do several different transformation operations. We'll have this flat map here, and that's going to give us a lambda here, which will then split the line up into the component words. And then the map is going to take the word, and it's going to replace that with a tuple of word and then the literal number 1. And then the reduce is going to then sum all of those ones there from the word, and it's going to basically create a count of the number of words. So you can see basically this is all on one line. Of course, we've broken it up for clarity into things, but we're going to now I'm going to do a shift enter operation to run that, and then I'm going to then do a collect operation, which is an action. And that action is going to run our operation, and then that's going to give us our results, which is here. So you see here we're getting an operation with a bunch of tuples, and that those tuples are going to give us the counts, which is the words that are in that file as well as the counts. In this case, no particular order because we didn't do any kind of sort. So you see here, for example, the word particular, as a matter of fact, has two counts in that. So this gives us kind of a hello world example. Now a lot of you are probably thinking, this isn't a big deal. I could write a 2-line Python program that easily do the same thing, and I don't even need Spark for it. And that's certainly true. This is a hello world kind of example, and we can do hello world in any language. Now, one thing that Spark is giving us, however, is that although in this case we loaded this from just a readme.md file, we could have loaded this from a Hadoop location with many, many gigabytes or even terabytes of data that could be distributed across a cluster. And we would be able to run it with the exact same code. Now, if we were to interface with a Hadoop cluster using a Python program, we could definitely do that, but it would be not transparent. I mean, this would be a lot of operations against the Hadoop API, and we'd be loading the data, and we would have to code a lot of this around Hadoop there, which we could do it certainly, but in the case of Spark, we're able to do that relatively transparently. So the same operation that works on a trivially small text file can then work on a big data component. So this is our word count example. So and we have this in IPython notebook that we're familiar with from our previous exercises. Now, we're going to be doing a lot more work here, a lot more than just word counting. We're going to be using MLlib and in Spark in order to do the same type of operations that we were doing with scikit-learn on the Python in Python. So there's some exciting stuff here, and I hope you are as excited as I am to continue forward to our next session. So thanks everyone for listening to this and your interest.